Hey everybody, let's talk about engineering materials. Engineering materials are typically divided into four major categories: metals, polymers, ceramics, and composites. Each of these materials has unique properties, and understanding how to use them efficiently is key to successful engineering. Today, we're going to focus on metals, their structure at the atomic level, and how various techniques such as alloying and heat treatment can improve their properties. Now, metals are essential to many engineering applications, but not all metals are created equal. Among the most important for engineers are iron, aluminum, titanium, magnesium, copper, and nickel. Iron is arguably the most important because it forms the basis for steel, a material that is both strong and versatile. It's used in everything from buildings and infrastructure to tools and machinery. Aluminum is widely used for its high strength to weight ratio, making it ideal for applications where weight is a critical factor, such as in aerospace industry. It also has a relatively low melting point, which makes it easy to cast into shapes. Titanium shares many of the same properties as aluminum, but it's even stronger and can withstand higher temperatures. This makes titanium a popular choice for high-performance applications, especially in aerospace and medical industries. However, it's more expensive and harder to process than aluminum. Magnesium is another lightweight metal used in specialized applications, often in the automotive and aerospace sectors. And lastly, copper is known for its excellent electrical conductivity, making it essential for electrical wiring and electronic components. Each of those metals has its own set of advantages, and it is used in different engineering fields based on scientific requirements like strength, weight, and conductivity. So, to truly understand how metals work, we need to look at their structure at atomic level. Atoms in metals are arranged in regular repeating patterns, forming what is known as crystal lattice. This regular arrangement makes metals crystalline materials, unlike materials such as glass, which have a more random atomic structure. There are different types of crystals lattices in metal, and each metal has its own preference. For example, copper has a face-centered cubic structure, where atoms are located at corners and the center of each face of the unit cell. Iron adopts a body-centered cubic structure, where there's one atom in the center of the unit cell, and which makes iron more rigid than copper. Titanium forms a hexagonal close-packed structure, which is more complex but provides titanium with its unique strength-to-weight ratio. These differences in atomic arrangements affect the properties of the metal, such as their density, strength, and how easily they can be shaped or deformed. No metal lattice is perfect. Real-world metal structures often contain defects that can significantly influence their behavior. These defects can include vacancies, where an atom is missing from the lattice, interstitial defects, where an extra atom is squeezed into the space between the regular atoms in the lattice, and substitutional defects, where an atom is replaced by a different atom of another element. These type of defects can impact the mechanical properties of metals, such as strength and ductility. Additionally, metals can have dislocations, which are defects where rows of atoms are shifted. Dislocations can move through the lattice when stress is applied, and this movement is one of the primary ways metals deform. One of the main goals in metallurgy is to improve the strength of metals. This can be achieved through various techniques. Grain boundary strengthening. The metal structure consists of different grains, which are regions of crystal lattices aligned in different directions. The smaller grains, the stronger the material. By controlling the cooling process of materials, we can control the size of these grains and strengthen the material. Next, work hardening. By deforming the metal, we can increase the number of dislocations in the structure, which makes it harder for the dislocations to move and improves the metal's strength. However, this also reduces the metal's ductility, making it less flexible. Next, alloying. Adding other elements to a metal to form an alloy is another way to improve its properties. For instance, adding carbon to iron forms steel, which is much stronger than pure iron. Other alloying elements like chromium and stainless steel can improve the resistance to corrosion. So, in addition to alloying, metals can be treated with heat to improve their properties. Common heat treatment processes include quenching, which is rapidly cooling the metal form a high temperature to increase hardness, and tempering, which is reheating the metal after quenching to reduce bitterness and increase toughness. So, by carefully controlling the temperature and the rate of cooling, engineers can manipulate the metal's microstructure to achieve the desired combination of strength, hardness, and ductility. Well, in engineering, metals plays a crucial role in the design and construction of virtually everything. Understanding their atomic structure, defects, and various techniques to improve their properties is fundamental for creating materials we rely on daily. Metals like steel, aluminum, and titanium continue to shape the world around us, enabling everything from skyscrapers to airplanes. So, by exploring the concepts between science and materials, engineers can ensure these materials remain at the heart of innovation. Well, thank you for watching, and I hope you gained some insight into the fascinating world of metals and their properties. See you in the next videos.